Hi everyone, welcome back to chemistry. In this video, we're going to continue talking about moles, specifically moles in chemical equations. So anytime we're dealing with a balanced chemical equation, I said that when, for example, looking down here, if we look at our chemical equation, the coefficients, right, the numbers in front of each of our different chemical species, I said that that tells you the ratio that these different chemical species react in. Right? So I said, right, if we put in 2 atoms of sodium and 1 Cl2 molecule, we're going to get out 2 NaCl or 2 sodium chlorides. Right? That's the ratio that this reaction occurs in. But what I didn't tell you, because we didn't know anything about moles yet, is that those coefficients actually also tell you the molar amounts for each of those chemical substances. So for instance, while I could say 2 moles of sodium react with 1 molecule of Cl2 to produce 2 formula units of NaCl, I could also say 2 moles of sodium react with 1 mole of Cl2 to produce 2 moles of NaCl. So these coefficients actually refer to the number of moles of each of those different chemical species that you have. And this is really cool because we can use these mole ratios, and that's what they're sometimes referred to as, mole ratios, in the chemical equation as conversion factors. Okay, so we can say, all right, well, I know that if I put in, right, 2 moles of Na and 1 mole of Cl2, I'm going to get out 2 moles of NaCl. And so we can split up these different mole ratios, the ratio these moles of each of these chemical species reacts in, we can split those up into conversion factors. So we can say, okay, looking at just my Na and my Cl2, right, just these two, what is the ratio those react in? Well, it's a 2 moles to 1 mole ratio, 2 moles of Na and 1 mole of Cl2. And so I can write a conversion factor from that. Where I have 2 moles of Na on top and 1 mole of Cl2 on the bottom. And remember, with any conversion factor, you can always flip it, right? Depending on where you want to eventually get to, right? If I want to end up with moles of Na, I'm going to want that one on the top. If I want to end up with moles of Cl2, I'm going to want that one on the top. Okay, so these are 2 different conversion factors that I can write just by looking at this chemical equation, this balanced chemical equation. And that's the most important part, right? This has to be balanced. It has to be a balanced chemical equation. Otherwise, the ratio that they're reacting in is not going to be correct. And those mole ratios, these here, are going to be off. All right, so you can do that with other parts of the chemical equation as well. You can say, okay, now I want to look at just sodium and NaCl. I want to look at the relationship between those 2 things. I want to look at the mole ratio. And I'm going to write 2 conversion factors from just those 2, so the ratio they react in. Well, if I put in 2 moles of Na, I'm going to get out 2 moles of NaCl. Right? That's the mole ratio from my balanced chemical equation. I can also say I'm going to flip that, and I'm going to have moles of NaCl on the top and moles of Na on the bottom. There's a whole other piece, right, in this chemical equation where we can look at just Cl2 and just NaCl, and we can look at that relationship and say, okay, if I put in 1 mole of Cl2, I'm going to get out 2 moles of NaCl, and vice versa, right? So let's see this in action. So this question says, how many moles of Cl2 react with Na, sodium, to produce 5.8 moles of NaCl? All right, how many moles of Cl2 from 5.8 moles of NaCl? So I'm given this 5.8 moles of NaCl, and I want to convert to moles of Cl2. Now, if I want to get from moles of one substance to moles of another substance, the only way to do that is using a balanced chemical equation. That's the only thing that's going to connect moles of one thing to moles of another thing. is that balanced chemical equation. Just like we said, the only thing that's going to connect grams to moles is the molar mass. The only thing that's going to connect moles of A to moles of B is your balanced chemical equation. Okay, well, luckily we have a balanced chemical equation, and you do always want to double check that it's balanced. This one looks like it is, right? We've got 2 atoms of Na and 2 atoms of chlorine, and then at the end we have 2 Nas and 2 Cls. So it is balanced, so that's great. All right, so as always, we're going to start with what we're given. Anytime we're converting, we're going to start with what we're given, which is 5.8 moles of NaCl. That's what I start with. And then I know I'm going to need a conversion factor because we're converting. So I need some kind of conversion factor to get me from one thing to the next thing, to the next unit. So moles of NaCl is in the numerator here. So where does moles of NaCl need to go? Yeah, in the denominator. For now, I'm just writing moles of NaCl, and we'll figure out how many moles in a second. All right. Now, if I want to cancel out those moles of NaCl, the reason I want to do that is so that I can end up in moles of Cl2. So we can put moles of Cl2 on the top. And now it's a matter of filling out this part. How many moles of Cl2 react to form how many moles of NaCl? And that comes from your mole ratio, which is in your balanced chemical equation. Sometimes I'll abbreviate equation EQN. All right, so what is the molar ratio between these two things? What goes on top? Yeah, 1 mole of Cl2, right? I get that from the coefficient here. It's an imaginary one. We don't see it, but it's there. And then what goes on the bottom? Yeah, 2 moles of NaCl from this coefficient here, right? Let me color code that actually. Okay, that's the ratio these things react in. That's the mole ratio. Okay, so now it's a matter of we can cross out our moles of NaCl, and we're left with moles of Cl2, which is great because that was our whole goal, was to get to moles of Cl2. Okay, so we can do this calculation. It's going to give us 2.9 moles of Cl2, remembering always to keep your units and tell me what you have, right? Moles of what? Cl2. All right, let's try this again. So this one says, consider the reaction below. So we have a new reaction now. How many moles of H2 react with N2 to produce 14.3 moles of NH3? All right, so what are we given in this problem? Yeah, we're given this number 14.3. We're trying to make 14.3 moles of NH3. So that's going to be our first kind of train track. And then what comes next is going to be some kind of conversion factor. Now, we want to get from moles of NH3 to what? What's our goal here? Moles of H2. Okay, moles of H2. How many moles of H2 do I need to react with N2 to produce 14.3 moles of NH3? So the only pieces here that we actually care about are H2 and NH3. That's the only mole ratio, or the relationship between those two is the only relationship we care about, because N2 is just existing there, right? It's not asking for how many moles of N2 you're going to react. It's just asking for how many moles of H2. So we're going to ignore that one for now. And we're just going to think about the relationship between these two things. Oops, these two things. All right, so what is the relationship between those two things? Well, it looks like, right, from our balanced equation, we can say 3 moles of H2 go in and 2 moles of NH3 come out. So that's our molar ratio, right? 3 to 2. Now, we know 3 moles of H2 produces 2 moles of NH3, but which one goes on the top, moles of NH3 or moles of H2? Yeah, moles of H2, moles of H2 needs to go on the top. Why? Yeah, we want to get to moles of H2. That's our goal, right? So it needs to be on the top right of our conversion problem. Okay, so on the bottom, what goes on the bottom? Yeah, 2 moles of NH3. Why 2 moles? Yeah, from our balanced chemical equation. That's the ratio these two things react in. Remember, I'm going from moles to moles. The only way to do that is with a balanced chemical equation. Okay. All right, so let's see here. We got 14.3 times 3 divided by 2. 14.3 times 3. And that's going to give me 21.5 moles of what? Yeah, H2. Remember, these canceled out. Okay, and we're left with moles of H2. All right, so I rounded to 3 sig figs in my final answer because my measured value has 3 sig figs. Why didn't I round to 1? I mean, these both have just 1, right? Well, the reason is because these are considered exact. Because those numbers are ratios, right? It's almost like when you have, counted values, right? I have 4 apples. Well, there's no measurement there. You're just counting the number of apples you have. You're not taking a measurement with a ruler that has some error in it because you have tick marks you're looking at and estimating, right? So it's not a measured value, it's exact for any time you're looking at these mole ratios. So you can essentially ignore that for sig figs, and you just look at the first measured value for sig figs. So we've talked about how we go from moles of one substance to grams of one substance, right? Using the molar mass. Talked about that in the last video. And we've talked about how we go from moles of one substance to moles of another substance, right? Using the mole ratio. That's what we talked about in this video. But what if you need to go through all 3 of those steps? And you can go both ways on this, okay? What if you want to go from grams of B to moles of B to moles of A? Or moles of A to moles of B to grams of B? What if we want to do that? Well, we can. So let's try this out. So a chemist has 8.3 moles of Cl2. How many grams of Na can react with that amount of Cl2? Okay, so what is this question asking? Well, we are in moles of Cl2. And we want to get to, what do we want to get to? Grams of Na. Do we know a way to get from moles of A to grams of B in one step? Can I just use the molar mass of Cl2? No, we can't, right? Because the molar mass of Cl2 connects grams and moles of Cl2, right? Grams of Cl2 to moles of Cl2. It doesn't connect moles of Cl2 to grams of Na, right? We can't do that, but we can do it in a couple steps. So we know we can get from moles of Cl2 to moles of Na as long as we have a balanced chemical equation that connects those two things. And we do, right? We have Na here, 2 moles of Na go in, and 1 mole of Cl2 goes in, right? Why am I only looking at Na and Cl2? Well, those are the only things that we care about for this problem. Okay, so we know how to get from moles of Cl2 to moles of Na. How do we do that? Well, that's going to be our mole ratio from our balanced equation. Now, to get from grams of Na from moles of Na to grams of Na, how do we do that? Well, yeah, that's going to be our molar mass, right? Molar mass, the grams per mole. So we can't go in one step, but we can go in this alternate route, right? Going this way. So let's do that. So we are in moles of Cl2. Specifically, we're given 8.30 moles of Cl2. So that's our first train track. That's the only thing we're given here, is that we start with that many moles. And now we want to get to moles of Na, right? That's our next step in our kind of plan here. So how do we get from moles of one thing to moles of another thing? Yeah, the mole ratio in our balanced chemical equation. Okay, so what is the mole ratio between Na and Cl2? Let's write that actually over here as a little side quest. How many moles of Na and how many moles of Cl2 for our molar ratio? Well, it looks like if we put in 2 moles of Na, we also need to put in 1 mole of Cl2. And remember, I've just written a conversion factor. But that conversion factor, you can flip it, right, if you need to. So for this case, do we want to flip it or do we want to use it as is? Yeah, kind of led the witness there. We're gonna use it as is because we want to cancel out those moles. So 1 mole, should be 1 mole of Cl2, and then 2 moles of Na on the top. All right, so now we can cancel out our moles of Cl2, and we're left with moles of Na. Are we done? No, right? We don't want to get to moles of Na. We want to get to grams of Na. So we got one more step, but that's okay. We can do it. So let's see. We said we need to use the molar mass to get from moles to grams of our Na. So what is the molar mass of Na? Well, let's do that over here as a side note again. So molar mass, Na, we'll just do that here. Well, we only have one Na atom, so I'm just going to put 1 times to multiply, but we're not really going to have to multiply because we only have 1. And that looks like 22.990 on my periodic table. Grams per mole, right? Don't forget those units. Those are really important because they're going to kind of give you a clue as to how you're going to put that in this problem. So 1.220 grams per mole. And I actually want to rewrite this as grams per mole, like that. And that might clue you in to a fraction you can make or a conversion factor you can make out of this. So we could write 2 conversion factors from this. We could say we have 22.990 grams of Na per 1 mole of Na. Or we could flip it, right? Taking this and making a conversion factor out of it. You could think of it as extending this line here, and it is. All right, but you can flip it as well, depending on what you want in your equation or in your problem. So for here, we're in moles of Na, and we want to get to grams of Na. So what do we want to put on top, moles of Na or grams of Na? Yeah, grams of Na, because we don't want to cancel that out. We want to cancel out moles of Na. All right, so 1 mole of Na goes on the bottom. Why 1 mole? Yeah, there's an imaginary 1 down here. 1 mole, grams per 1 mole of our substance. All right, so now let's cancel out those moles of Na. I'm just zooming out here. Actually, let me scoot this over a bit. I have a little bit more room here. And now we got to do that calculation. So we're going to multiply everything on the top and then divide by the product of everything on the bottom. Okay, so 8.30 times 2 times 22.990. And then looks like that's just divided by 1, so we don't have to even do that. So we got 381.634 grams of sodium. And let's see, this is an exact ratio, right? So that's considered exact. This one has, that actually has 5 sig figs, right? 5 sig figs. And this one has 3 sig figs. So we want our final answer to have 3 sig figs, so we need to round to that digit. So let's go 382 grams of Na. 382. So if we put in 8.30 moles of Cl2, we can make 382 grams of sodium. Now, why would we want to figure this out? Why would we even need to solve a problem like this? Well, this is actually how chemists figure out how many grams of different substances they need to add when they're doing chemical reactions, right? I don't have some kind of molimeter where I can determine from my balanced equation, I need 2 moles of this and 2 moles of this other thing. I don't have anything to measure that, but I do have a scale in the lab that I can measure out how many grams of sodium I need. And that's when this comes in handy. So let's try this one last problem. So this says a chemist starts with 15.0 moles of C2H4. How many grams of CO2 will form? All right, so let's go ahead and just write out right away. We start with what we're given, 15.0 moles of C2H4. And we want to get to grams of CO2. Do we know anything that connects moles of one thing to grams of another thing in one step? No, I don't have any way of doing that in one step, unfortunately. I wish we did. So we got to do a couple steps. So what I'm thinking is, how about, well, I know something that connects grams of CO2 to moles of CO2, and that's going to be our molar mass of CO2. And I know something that connects moles of C2H4 and moles of CO2, and that's going to be our mole ratio from EQN, from our equation, right here. Okay, so I can't go in one step, but I can go this alternate route, right? I can go that way. So let's do that. So we've got moles of C2H4 to start with, and we want to know, okay, what's the ratio between, the mole ratio between C2H4 and CO2, just looking at those two things. So for now, you can pretend these don't exist. We don't actually need them for this problem. Okay, so just ignore them in your brain. All right, so looks like we have 2 moles of C2H4 is going to produce 4 moles of CO2. Again, remember, looking at our coefficients to get those moles. Okay, so 2 moles of C2H4. We want to put that one on the bottom, right? Why did I want to put it on the bottom? Yeah, I want to cancel it out, right? So if 2 moles of CH4 goes on the bottom, then 4 moles of CO2 goes on the top, right? Those are the two things we're looking at. Those two things, the relationship between those two things. And actually, let me keep this color-coded. And now we can cancel out moles of C2H4, and we're left with moles of CO2. Now, are we done? Do we want to end up in moles of CO2? We don't, right? We want to end up in grams of CO2. So we've done the first step, and now we got to do the next step. And the next step involves our molar mass. So we got to figure out our molar mass of CO2. So let's do a side quest over here for our molar mass. All right, so we've got 1 carbon, and we've got 2 oxygens. Carbon has a mass of 12.011 grams per mole. And oxygen has a molar mass of 15.999 grams per mole. So you got to total that up. And that's going to give us 44.009 grams per mole. And now remember, actually let me write this like this, grams per mole. So now we can create our conversion factor here, where we have what on top and what on the bottom. Well, we want to end up in grams of CO2. That's our goal. So I'm going to put grams of CO2 on top. And then on the bottom, we're going to have moles of CO2. Now, we got to figure out how many of each of these things. So how many grams of CO2? Yeah, 44.009 grams per every 1 mole. So 44.009 grams per every 1 mole. Grams per mole. All right, now we can cancel out those moles of CO2, and we're left with grams of CO2, which is great because that was our goal, right? That was our goal. All right, and then it's just a matter of doing the calculation. So we're going to multiply all of the numbers on the top and then divide by the product of all the numbers on the bottom. So when I'm entering this into my calculator, I'm going to do 15.0 times 4 times 44.009 equals, and then I'm going to divide by 2. And that's going to give me 1320.009 0.27 grams of CO2. And now let's just double check our sig figs. So here we've got 3 sig figs, and generally you're probably going to look at this first train track to get your number of sig figs, because that's typically the measured value. But let's just double check. This is exact because it's a ratio. And then this one has 1, 2, 3, 4, 5 sig figs. So we will say we've got around 2, 3 sig figs, which is going to give us 1320 or 1,320 grams of CO2. Quite a lot of grams of CO2. All right, that's it for this video. I'll see you in the next one to talk about mass-to-mass problems.